Hello again, everybody. Let's continue our discussion from last time. Uh, we had just solved some basic trig equations using our calculator. We still found two answers, but let's see if we can put this into a formula. Well, within the range, again, I'm using this interchangeable here, but what I really mean is just the interval that I'm working with. Within the range from 0 to 360 degree or 0 to 2 pi, for basic trig functions of sine and cosine, the way we think about this is for sine of x, we found our first answer by using the inverse trig function. So theta 1 equals to sine inverse of x. And to find the second one, again, because of symmetry, we can do pi minus theta 1. Okay, and you can see on the bottom graph, right, the symmetry of the first and second quadrant is, well, it's in the picture. So theta 1 rotating up this way, but that's the same as starting from pi and rotate negative degree, right? Negative theta 1. That's where this pi minus theta 1 come from. So starting at pi, rotate negative theta. Similarly, in the symmetry of quadrant 4 and quadrant 3, same idea. Our theta 1 is going in this direction for quadrant 4, and then the symmetry is starting at pi, kind of rotating this direction. Okay, and this is really all we have to worry about because the inverse function for sine, right, sine inverse, only have output answers in the quadrant 1 and quadrant 4. So these two are the only possibility. Similarly, going into cosine, uh, same idea. We find our first answer by doing cosine inverse of x, get our first angle, right, whether in degree or radian, and then to get the second angle, we leverage symmetry again. And the formula we have here is 2 pi minus theta 1. Actually, since I already listed here, I might as well write it down again. Or 360 degree minus theta 1, right? Again, depending on whichever unit. Same thing here. Or 180 degree minus theta 1. Okay, and we can see the symmetry here in kind of the same light. If we are working in quadrant 1, right, theta 1 is in quadrant 1, we rotate this way, and to get uh, theta 2, we start at here, which is not 0, but 360 degree, and then we subtract theta 1. Okay. Similarly, if theta 1 is all the way in quadrant 2, that means we're going all the way here. Okay, we can still just rotate from 360 degree, rotate backwards, right? The same theta, right? Hence negative theta 1, and that is going to get to our theta 2, right? So this formula does work for the corresponding uh, range of the angles that we're working on. The big deal that you have to kind of remember is whenever you're working with angles outside of this range, we have to bring them back into the correct range by using the concept of coterminal angles. And this concept is going to be with us essentially forever, so you might as well get used to it, right? Everything we talked about happens on uh, the interval from 0 to 360 or 0 to 2 pi, but then everything else can be brought back using coterminal angles. Okay. Now, finally, we kind of suspected this all along. We have this cancellation property, but it's not quite as clean as we've seen it before. It is not quite as clean because of the domain and the range issue, right, from the corresponding, trig function and trig inverse. But at least we have some sort of cancellation. Here we go. Uh, Sine and sine inverse, right? In this case, we have sine inverse on the inside of the function. This always cancels. Basically, the cancellation property works flawlessly here, no problem. But that's mainly due to the fact that the input or domain for sine inverse is very limited. So this all valid x is really just the interval from -1 to 1. Okay, so it sounds nice and all, but it turns out, well, it's a very limited interval. The flip side of that coin is when you have sine theta on the inside. Well, this is slightly bit of a problem just because the domain for sine is all real numbers. So there's no limitation on the domain. But the output of sine inverse is very limited. So we have to find a way to make our restriction. So this is kind of why I emphasized on the idea of coterminality before. For the range between 0 and 2 pi, or again 0 to 360, 0 degree to 360, basically on the normal range that we work on, theta, this sine theta is still, a pretty wide range of possibilities here, but at least it limits our options. Basically, using the previous formulas, we're either working with theta or pi minus theta. And the choice is because whichever one is in the output of sine inverse, which is either in quadrant 1 or quadrant 4. Okay, so whatever its input angle, right, whatever the theta is, you don't automatically get to say it's equal to theta, just because it could very likely be outside of the range for sine inverse. But if you do theta, if you minus theta from pi, then you have one of the two options, and this is going to work. One of these is going to work. One of these is going to fall into quadrant 1 or quadrant 4, okay, as we've seen it before. So kind of go back real quick. If you have an answer already in quadrant 1, then you're good to go. If you answer in quadrant 4, also good to go. But if you have a quadrant in, if you have an answer in quadrant 2, for example, then pi minus quadrant, pi minus this answer is going to give you back into quadrant 1. Similarly, if you have an answer in quadrant 3, pi minus this answer is going to land you back in quadrant 4. Okay. The only thing you do have to adjust is, once again, you can't never outrun this, is by leveraging the coterminal angle to bring that answer, which is in quadrant 1 quadrant 4, back into the right range from negative pi over 2 to pi over 2, or negative 90 degrees to 90 degrees. Okay. Similarly, for cosine combination, same idea. The one with cosine inverse on the inside cancel out flawlessly. But again, that's just because this x is very limited, right? The domain for cosine inverse is also -1 to 1, so that one's too kind of easy to remember. But for the same condition, cosine inverse on the outside, right? This case with cosine theta on the inside here. This case, we're either working with theta or 2 pi minus theta. Okay, and the requirement here is depending on whichever is in theta 1 or actually war is probably better than and, or theta 2. I'm going to change that to a war as well. Obviously, it cannot be in both, but this way of description is better. Okay, so that's basically it for this quote unquote cancellation. Now, you do have to use coterminal angle multiple times in some circumstances. If you are given a really big angle, right? If you plug in, let's say, cosine of 1000 degree in here, you have to use the idea of coterminal angle to bring it back into the appropriate range first, and then you can use this trick. And then afterwards, that result might still be outside of the range from 0 to 360, which then you apply coterminal angle one more time to bring it back into the right place. Just make sure you double check that it is in these quadrants, okay, in the appropriate quadrants. Okay, I'll let you kind of try that on your own here, but this is really not a hard thing for you to check. Well, in the meantime, let's go ahead and move on. The more interesting situation is when you interact a trig function and the inverse trig function that's not directly the inverse of the trig function you're working with. So in this case, cosine of arctangent of 3 over 4. Now here, the question typically will say find the exact value, because I don't want you to just punch it in to a calculator and give me some stupid decimal, right? That's not what I want. Well, how do we do this the quote unquote the right way? Well, it's kind of the same idea as before, but if this is kind of a confusing little question, how about we bring it back into something that we're somewhat more familiar with? Well, to do that, I recognize this connection one more time. I'm thinking to myself, well, this arc tangent that inputs a length, as we can see, the 3 over 4, is going to output some angle theta. So if I just go ahead and just, for a quick second, I know this is going to become some angle, so just let it be theta. Then this problem really just become cosine of theta. Okay. Now, I don't have any idea what cosine of theta is. I don't even know what theta is, uh, in terms of numbers. But at least that's what the question turned out to be. So now let's work on what theta means. Arctangent of 3 over 4 equals to theta. Well, what this means here is that when you input the length 3 over 4 into arctangent, I get some angle theta, right? Obviously. Well, if we're not familiar with the inverse trig function, let's bring it back into the trig function. This means, by definition, that 3 over 4 is equal to tangent of theta. Hey, all of a sudden, now things are beginning to kind of ring the bell, because what we're saying here is, given tangent theta equals to 3 over 4, find cosine of theta. I'm hoping you recognize this problem to be somewhere of a familiar problem, because previously we're saying given 3 over 4 equals to a trig function, find the rest of the 5 trigonometric ratios. While here, you're actually only asked to find one. This is how we can bring a question back into a problem that we already know how to do. And you guys know this by now. We're going to construct our right triangle. Okay, label your data and draw the mark for the right angle. Tangent is opposite over adjacent. Okay, all we need to do is to solve for this hypotenuse by using the Pythagorean theorem, which is h squared equals to 3 squared plus 4 squared. 3 squared is 9, 4 squared is 16. Add that together is 25. Therefore, h is square root of 25, so h is 5. Okay. Now, as soon as I finish writing that 5, as soon as I completed my triangle, then going back to the question, what is cosine of theta, becomes a very easy question. Because now cosine is adjacent over hypotenuse, therefore the answer is simply 4 over 5. And that is the exact answer. Okay. Now, when you are working with this kind of answers, you can get an exact answer even with a calculator. In fact, if you go ahead and punch that into the calculator, punch this thing into the calculator, you're going to get 0.8, which is 4 over 5 in the exact answers. But in general, it doesn't work out as nicely. So to find the exact answers, you have to use this method. Okay. Well, let's try another one. It's the same idea, similar idea here. We're going to go ahead and take that inside part but let that be theta. After doing so, the question becomes cotangent of theta. Well, start with cosecant inverse of 9/5 equals to theta. If you apply the definition here, then 9/5 is equal to cosecant theta. From here, we draw our triangle. Theta, while cosecant is hypotenuse over opposite. So now if I have adjacent side, right, by Pythagorean theorem, I'll have 9 squared equals to 5 squared plus a squared. 9 squared is 81, 5 squared is 25 plus a squared, minus 25 on both sides. 81 minus 25 looks like 56 equals to a squared. And of course, we take the square root on both sides. A is just equal to square root of 56. Okay. Again, once we complete our triangle, then this problem becomes very easy. Cotangent is adjacent over opposite. So the answer is just radical 56 all over 5. Okay. So here is where you have to basically use a method like this to tackle this kind of problem. Otherwise, when you punch that into the calculator, it just gonna give you some long decimal answers, right? And then there's no way for you to guess that long decimal answer to be radical 56 over 5. This is not something that us humans do. So this method is probably the best way, and it's really efficient and universal. There are other ways by using the Pythagorean identity, right? But it's the same issue as we mentioned before. You have to have exactly the one uh, that's mentioned in the Pythagorean identity here. In this particular case, we do have cotangent and cosecant, which is both mentioned in one of the Pythagorean identities, but that's not always going to be the case, right? For example, here in this case, cosine and tangent, right? These are not mentioned in the same Pythagorean identity, so it actually takes more work. And while that method is somewhat viable, this is the method, this triangle method is going to be the one that we're going to focus in class. Okay? Now, if you're thinking, why not just put it in the calculator? What's the point of this? Well, I guess a calculator can do a lot of things, right? But one of the things that we actually want to do is leverage this technique to kind of manipulate to the next step and work with expressions only. Well, in that case, you can't hope to have a calculator that's going to solve your problem for you. Well, that's this example right here. This is one of the key examples we're going to leverage throughout this rest of the semester. We're going to write the following expression into an algebraic expression that involves x only. An algebraic expression is something that essentially doesn't involve any trigonometry, right? Trig or inverse trig. Addition, subtraction, multiplication, division, exponent, sometimes even radicals. All of these are algebraic expressions. Okay. Basically, what I mean here is by the end of the process, end of the solution, I don't want to see any trig functions. Okay, here we go. The way we tackle this problem is really the exact same idea as before. In some sense, it might even be a little easier. Well, idea here is same thing as before. Take that inverse trig function and let that be theta. If I do that, then the question becomes sine of theta. Well, from here though, I have secant inverse of x over 2 equals to theta. And by definition, that means x over 2 equals to secant of theta. I'm going to construct my triangle here. And secant of theta is hypotenuse over adjacent. So I'm really looking for the opposite. Okay? Again, I'm going to use the letter B just because O is too hard to write to differentiate from the letter 0, the number 0. But this is where the first mistake, the first common mistake tend to happen. Well, let's write this out. By Pythagorean theorem, I have x squared equals to 2 squared plus b squared. Now, when I'm writing it here with the color code and everything, it is, it's not too hard to do. But just for the sake of example, if you write this right on your own papers and pen, papers and pencil, very likely it's going to look like this. And the problem here is, what are we actually solving for? Well, we're so used to, or really we're conditioned to solve for x. But in this case, I don't actually want to solve for x, right? What I want to solve for is the b. I want to write b as the expression involving x. Okay, so going back to the, for the colors, I actually want to solve for b, not the x. Be a little bit careful here. Well, this is just x squared equals to 2 squared is 4 plus b squared minus 4 on both sides. I have x squared minus 4 equals to b squared. And of course, to get b, I take the square root of both sides. This is mistake number 2, a very common mistake number 2, is where people say b is equal to x minus 2. Well, it ain't, right? It does not, because you cannot square root over subtraction here, okay? There's nothing you can cancel here. There's nothing you can cancel, so this is false. Okay, this is false. Okay, do not cancel. What that means here, though, is actually even nicer, in my opinion. You can just leave your answer exactly how you see it, x squared minus 4. Okay? Moral of the story, guys, is that don't do things you're not asked to do, right? So do not simplify here. You want to write b exactly as some sort of expression of x, okay? Because now I have completed my triangle. Let's move it a little bit further. Okay, now I've completed my triangle. Therefore, I go back to the question sine theta. Well, sine theta is using this triangle, and sine is opposite over hypotenuse. That means our answer is square root of x squared minus 4 all over x. And this is my final answer. Okay, you see that answer does not involve trig function or inverse trig function whatsoever. It's just an algebraic expression of x. And we can also see that this algebraic expression is so much easier to use than this answer, right? If I want to plug in a bunch of numbers, I'm going to prefer this over this any day of the week. Okay? When it comes to simplification, if it involves other things, like you will see in Calc 2, a bunch of these things in Calc 2, I'm going to involve this, right? I prefer to use that over this, again, any day of the week. By the way, you'll see, hopefully, both of these in this kind of topic in Calc 1 and Calc 2. So I promise it's useful. Okay? Let's try this again. One more example. Back to the last example here. Really the same idea as before. Go ahead and let the inside part be data. Then the question turns into tangent of data. Working with data, we have arc sine 7 over x equals to data. By definition, this means 7 over x is equal to arc sine of data. Oops, that's a derp. It means sine of data. From here, draw my triangle. Here's data. Please label your data too when you're drawing the triangle, because your opposite adjacent side is depending on the location of your data. So if you don't draw it, I wouldn't be able to know, or anybody else, maybe even yourself, would not know which one is the actual adjacent, which one is the actual opposite side. Okay, so take a fraction of a second to label your data. Well, in that case, sine is opposite over hypotenuse. Okay? That means I'm looking for the adjacent side. Okay? Again, once we remember what we're actually after, we have x squared equals to 7 squared plus a squared. Well, x squared is x squared. 7 squared is 49 plus a squared is a squared. Minus 49 on both sides. I have x squared minus 49 equals to a squared. And we get a by square rooting both sides. Again, don't try to quote unquote simplify, because you will be wrong. So square root of x squared minus 49. And as soon as I complete my triangle here, going back to the previous question, tangent data, very simple, opposite over adjacent. So 7 over radical x squared minus 49. 94. 49. Okay, and that is the final answer for this problem. Really not hard of a problem. And if you take a look, the reason why I say this one's easier is what did we actually calculate? We didn't really calculate anything per se, right? The biggest, hardest calculation in this example, both of these examples, is, well, the square. That's the only number that we actually crunched out. In the previous one, at least we did a subtraction, which sometimes, admittedly, I will get that wrong. But hey, subtraction is hard, right? But you actually have to deal with more calculation in this type of problem versus these type of problem, where you're actually just more or less using the definition, pushing symbols around, and make sure you have your final expression in terms of x only. Okay, this concept will be important for us for quite a while and for various different part of the sections. So make sure you keep this one in mind. Okay, well, with that, we are completely done with this section. Hopefully everything is easier to follow, and make sure you practice this so when you see it in the future, this will not be anything new and anything too difficult. Okay, see you guys in the next video.